Well, hello again. This is Roger Koch Barr for Bioelectricity. We're in week 4, and this is the third segment in week 4. In this segment, we're talking about the specific way in which Hodgkin and Huxley replaced the membrane resistance with several ion channels. Let's get right into it. In the Hodgkin and Huxley model, the Hodgkin and Huxley model observes that the passive model is limited in its representation of the paths through the membrane that are caused by holes and channels in the membrane. In the passive model, all of that is put together into a single equivalent resistance represented by Rm. What Hodgkin and Huxley did is they replaced that composite resistive model with what it really is underneath the surface, so to speak. It is 3 different pathways, or actually it's thousands of each of 3 different kinds of channels, 1 for potassium, 1 for sodium, and 1 for everything else, so-called leakage. Let's look at each of these pathways in a little bit more detail. Each ionic pathway now comes into the representation with a battery in it. Wow, a battery. And these batteries have voltages that are the Nernst potential for the concentrations for that particular ion. So Ek is the battery in the K path. Ena is the battery in the sodium path. El is the battery in the leakage path. As you know, Ek and Ena are the equilibrium voltages for potassium and for sodium. As you know from the work we did in an earlier week, Ek is a negative number and Ena is a positive number. So these batteries have quite different voltages. That is to say, it may be so that the form of the path is similar. So this one, they all have the same elements, but the actual details of what's in there is quite different. So Ek is not equal to Ena, and that's not equal to El. These are 3 different numbers. We also need to notice that the resistance in each of these pathways is marked with a line through it. So here we have a line through that resistance, and that's a signifier that that resistance is a variable resistance. It's not the same resistance all the time. So there's a line through Gk, a line through Gna, and a line through Gl. These resistances are not linked to each other because a part of the model is that each of these 3 lines is operating independently. It's the so-called independence assumption. So that means that there has to be some other additional rules that tell us how these pathways operate. You'll notice in the way that these resistances are denoted here on the diagram that each of them is not actually written as a resistance, it's written as a conductance. It's reciprocal. So rather than having an Rk, Rna, and Rl, there is instead a Gk, Gna, Gl. I mean, at one level, it's just notational. It could have been done the other way. But here it has a little bit further significance because there are further equations that are given for these conductances. So what are exactly GK, GNA, and GL? Well, we'll come back in the next lecture and talk about those. Thank you for watching, and I'll see you again in a few minutes.